welcome to the presentation. So our topic is smart grid. My name is Usman Hassan and I am a PhD student in ECE department. Here are the contents of my presentation. Sorry. First of all, let us have an introduction to smart grid. So why do we need smart grid? The conventional grid is reaching its limits as we advance into the era of renewable energy sources.
Unit commitment and economic dispatch operations are unidirectional from consumers' point of view. Uh, what it means that in conventional grid, we do have unit commitment and economic dispatch operations, but they are initiated from the power provider side. It means that if we view from customer's point of view, customer has no control over these operations. And another thing is that the uh, conventional grid lacks automation capabilities. Although in some typical fault cases, fault can be resolved automatically, and there is some prediction based on short-term forecast. But customers cannot switch their loads to cheaper energy sources at any time using real-time market data, for example. So there are numerous definitions of smart grid. I will go by the definition in reference one. So a smart grid is an energy network that can automatically adjust to changes in demand and supply. It facilitates grid operators in planned integration of renewable energy by providing information on energy demand, which is then combined with weather forecast. With this forecast information combined with information on energy demand, uh, a smart grid can get a reasonable estimate of the energy to be generated. Using smart metering features of the smart grid, consumers can have reduced energy bills as their peak energy usage is shifted to low price models. A smart grid also allows energy producing customers to sell excess energy to the grid at times of maximal profit. I mean that the customers sell their energy to the grid at a time when profit is expected to be maximum. So conventionally also, if there are some independent like energy producers under some agreements, they can sell their energy to the grid, but they cannot do so at any time at will. So such a smart grid with features mentioned above would inevitably involve two-way communication between consumers and grid operators. So now what are some envisioned benefits of smart grid? So smart grid will result in improved generation and transmission efficiency. In general, because of a plethora of distributed energy sources, loads will be getting power. At least for some times, loads will be getting power from nearby generation sources. So this will result in a reduction of transmission losses. Similarly, many generating units will be no longer operating at full capacity just to serve the needs of a small load. So in this way, generation efficiency will increase. Furthermore, a smart grid will result in increased reliability as outages will be less when planning is based on short-term predictions. As I said earlier, that it would be possible in smart grid to dynamically switch load as per real-time demand and as per real-time market data. So smart grid is expected to have great automation capabilities, which can be also named as like self-healing capabilities. If there is a fault, it will be automatically detected and rectified by removal of faulty components and addition of like some routes. So this will eliminate the need to send maintenance teams at the spot of disturbance. So eventually the downtime of maintenance will be reduced and the revenue loss will also be reduced. Smart grid will delegate some control to customers. At least customers now will be able to purchase power from different sources, and they can do so depending upon their application specific need and at what time what application they are uh, using. So application can dictate, for example, which power quality is acceptable. Now, uh, instead of some selected power suppliers, there will be plenty of power suppliers in the market. Some will be uh, using like renewable energy sources, some will be generating energy from conventional sources. Overall, this will increase competition in the market and will result in fair prices. Smart grid is also expected to extend support for emerging technologies, the most popular being electric vehicles. There are many more benefits which have been presented earlier on by my other class fellows. Okay, now let us go through some technological aspects of smart grid. So smart grid is an engineering wonder and it spans across many disciplines. It is not possible to go through many technologies in one presentation. So I will go through just three main technologies. One is energy storage technologies. So distributed storage nodes will save energy at times of low demand and will supply energy at times of interruption or high demand. uh, Once again, use cases electric vehicles or EVs, which will greatly benefit from stored energy. So nowadays, the prevalent energy storage technologies are molten salt, which is a thermal form of storing energy. Then compressed air. Then we have lead acid battery, and then we have lithium ion battery. So lithium ion batteries are lightweight and they are energy dense, and therefore although further research is going on, but they are a promising candidate for smart grid. So as of 2019, the largest lithium ion battery had a capacity of 100 megawatts, and it was being used to augment a local grid in Australia. And I would also like to say that not only large storage capabilities will be required for smart grid, but the storage devices or the storage nodes must have the ability to uh, retrieve the energy at the rate uh, it, it is required of them to retrieve the energy. Interestingly, the electric vehicles themselves can serve as energy storage source. Some utilities are using retired EVs as secondary energy storage that aids the grid during power spikes. Now I will go through some communication technologies. So low latency communication using standardized protocols is important to enable the connection and disconnection of distributed energy sources in smart grid. So in general, a communication network is built over the power infrastructure, and this communication network can help in realization of demand response. Now, what is demand response? Demand response is adjusting electricity consumption in response to generation and market dynamics. So we can see a figure in this slide which presents a model of uh, DR realization with the help of a communication network. So first of all, what happens is that consumer data is either sent directly or through aggregators to meter data management system. So this meter data management system then forwards the data to our DR engine located in the local utility. So the DR engine now runs appropriate algorithms, and besides the consumer data received, it also uses the load forecast generated by load forecast module, and then it generates appropriate DR commands. And those DR commands, demand response control commands, are then relayed to the consumers and via a unidirectional link. The final decision making is taking place in the premise of utility by DR engine in this model at least. Okay, so now because of their ability to achieve more penetration with less hassle, wireless networks, aka wireless sensor networks, they provide greater degree of freedom in collecting and disseminating information in a smart grid. So again, we can see two figures in this slide. So on the left hand side, we can see a schematic which shows interaction among 7 smart grid domains. So in the bottom row, the domains are named after power infrastructure like bulk generation, transmission, distribution, and customer domains. And the top layer has 3 domains which which involve like management and decision making organizations and devices and systems, so like power markets, regional system operators, and service providers. So we can see that to ensure balance between demand and supply at all times, the power markets interact with all of the other six domains. Similarly, when a customer needs extra power, for example, so in addition to the customers being connected to the distribution network, they also have to communicate with power markets, regional system operators, and like local service providers. Now, what is on the right hand side? So the figure on the right hand side shows these seven domains expanded. So we can see there is some overlap between some domains, like transmission and distribution domains have some systems overlapping. So now within each domain, like within operations domain, systems and devices have similar functionalities and objectives. And typically, communications within a single domain, like all the communications happening within the markets or within service providers, they have like similar characteristics. Typically, they have the communication within a single domain have similar characteristics. Uh, that being said, we can see devices are actors with red boxes around them, so they are gateway actors, and the gateway actors are responsible for communication across the domains, and therefore they are required to obey interoperable protocols. Next, we will see a frequency monitoring network, abbreviated as FNET, in transmission systems. So in this slide, we can see again a schematic or a model that shows that how FNET and cognitive radio realize like frequency measurement with the help of a grid information network. So why frequency measurement is important? So the frequency measurement is important to stabilize frequency, which in turn ensures transient stability. So we can see FDRs. FDRs are like frequency disturbance recorders, which can be installed at various points in the power system, and then FDRs record forward their data to a FDR data concentrator. So the FNET data concentrator performs timestamp based ordering of the collected data and forwards these records to storage agents as well as control center for further processing. So the grid control center receives chronologically ordered frequency measurements from the data concentrator, and then it can perform its transient stability analysis. And for future record, a storage agent also can store this data. But we can also see a spectrum manager here. So what spectrum manager is doing, it implements cognitive radio or CR technology so that spectrum resources are shared. Cognitive radio technology basically means tapping into uh, free channels during transmission and receptions. So what has been proposed in recent literature is that we should, because of limited frequency resources, we should use cognitive radio technology in smart grid, wherein a transceiver can intelligently detect and move into vacant communication channels. So it is named as cognitive radio with dual architecture. What is meant by dual architecture is that the dual architecture keeps the spectrum sensing radio chain separate from the data transmitting transceiver chain, so that delay is minimal in transmission of time critical data during emergency situations. For example, there is a tornado and a big fault has occurred, and we are in need for a backhaul communication. So for this backhaul communication, we want the data to be transmitted quickly. So if we don't have dual architecture, then over a single link we will have to pause the data transmission so that we can sense the channels and we can like locate into vacant communication channels. Then we transmit for some time, then we again sense the channels and move into next vacant communication channels. So because instead of that, the dual radio architecture reserves the data transmitting radio chain separate from the spectrum sensing radio chain. Next, I will just name some control strategies. So like power quality control, to ensure power quality when some distributed sources are connected to boost the main grid are disconnected from the main grid after load is off peak, etc. Inverter based power control methods are available. They are called like voltage or frequency control, grid power connected PQ control. Now, what is droop control? The droop control method was primarily devised for the situations when a microgrid is operating in grid connected mode. So droop control is basically a current control strategy which ensures that the inverters exchange real and reactive power with an upstream network under the frequency and voltage constraint imposed at the point of common coupling by the main grid. Several other control techniques have been proposed in literature for smart grid like robust control, cyber physical system control, etc. So cyber physical system means that a smart grid has large number of like intelligent devices, and also it has a physical infrastructure, so we can treat it as a big CPS or a cyber physical system, and we can have like cyber code installed in the sensors which can perform control tasks. Now let us go through some main risks associated with smart grid. So smart grids will have like very large number of devices, even exceeding on a global scale. The number of devices in smart grid can exceed the number of devices in internet, for example. So uh, now the two types of devices, intelligent IT devices and conventional power devices, they have like different lifespans. IT devices age very rapidly, they need to be replaced. So if IT devices are being replaced quickly, they may lose compatibility with the power devices. So we may have to like replace power devices prematurely just to ensure compatibility with the IT devices. Less than ideal customers privacy, so customers data will be continuously being sent through smart meters or advanced metering infrastructure to utility, or customers will also be talking to like power markets and other stakeholders, and this will result in at least some of their information to be leaked, like at what time which customer uses which application, and which can be used to draw further conclusions like the income level of customer, etc. Security vulnerability because of sheer number of devices. So as I said that smart grid will have large number of devices. So when the number of devices is so much huge and there is no like central control, so at least there is always a possibility that one or a few devices will have no security protocol at all, and they will become weak points, and where at these weak points attacks can be launched like spoofing attack, denial of service attack, and whatnot. Physical vulnerability. So except from main generating units and utilities, many components of a smart grid will be not in some premises, rather they will be without physical premises, and this will make them liable to be stolen and manipulated. And last but not the least, uh, because of smart grid requiring expertise across different engineering domains, so we will have management teams with expertise uh, varying, and there may be difficulties in effective coordination between the management teams, which can result in potentially in poor decision making. So research is necessary to address these potential risks. Smart grid brings different electric energy producers and consumers into the fold of a large power market and enables consumers to become a part of decision making. Efficient communication and advanced control techniques are a must for smart grid. And further research on smart grids is a like a hot topic. Thank you. The main reference paper. Thank you.